Hello and welcome to this short tutorial video. We are in the process of reading this chapter number 15, on the topic of bridging the digital divide, so making Python and the Python ecosystem accessible to translators. And specifically in this chapter, there's a section on exercises, so we'll skip right to that one. So we'll skip right ahead to the section of exercises where we will specifically look at use case 1. So here we have exercises, and we will be looking at the first use case that is guided. So use case 4.1, calculating automatic machine translation quality evaluation scores. So in this use case, we want to perform an automatic MT quality evaluation using different types of metrics. So we're looking at string-based metrics such as BLEU and translation edit rate, as well as one embedding-based metric, which is BERT score. So we'll skip right into it. The way we can do this is obviously, multifold. So you can find different pages online to help you calculate these scores. Maybe you already have a pipeline for this, or you can look up different ways of calculating it. The way we will run through this here is that we use an AI system as a tool to help us to calculate these scores, what these scores even mean, and to compare them as well. So we will start with the first ones. So first we'll look at BLEU, then at TER, and then at BERT score. And what we need to calculate the automatic quality evaluation score for these metrics is we need two sentences. So first of all, here we need the human reference translation, and we need a machine translation output, which is often referred to as the hypothesis or the candidate sentence. And we want to compare how close in meaning and in quality in general is the machine translation output, is the hypothesis, to the human reference. So we consider the human reference translation to be the gold standard, and we want to compare how well the machine translation output is in comparison to that. So we will do this in a Colab notebook, which is very accessible. So you can open, if you have a Google account, you can open a Colab notebook. You can Google it straight away, or you can open it in your Drive folder. And then once we have this Colab, once we open a Colab notebook, this is the first thing you would see. I have it as a black screen. For you, it might appear in white. So the first thing that you could do is use Gemini straight away, right? Which is the AI model, the LLM from Google. So you could type it right here. What can I help you build? So you could ask how to do this right here in Gemini. I will not use that, but you can try it in here. So if you cancel this, or if you just click to notebook, then this is how the notebook will look. So we'll start with this, where here we can type code. We can also add text. We can add more code blocks. We can run the cells. But okay, let's pretend we don't know where we're even starting. We have no idea how to even go ahead with this. So we will go to an LLM of your choosing. So I will use Claude for this. You're welcome to use Gemini, ChatGPT, any other model that you would like. So let's have a think. We need help in calculating a BLEU score. So we'd like to calculate an MT quality evaluation score based on metric BLEU. How can I do this? And also maybe we would add, actually in my Colab notebook, because that might differ also if you're in a different environment, obviously, or if you're using Python or not. So now the system straight away knows where we are and what we want to do. Very simple. Obviously, you can define your prompts to be more complicated, but we can start like this. So it starts to give us a quick description of what BLEU is. So a bilingual evaluation understudy. It's a classic MT evaluation metric, probably the most classic metric. And then it tells us exactly how to do it in Colab, and already what to keep in mind. So that's perfect. So often we have to install libraries and import packages in a system. So let's just go through it step by step. We can copy this first library that we need to import. You can just click the copy cell. We paste it right in here. In Colab Notebooks, often you need the exclamation mark in front. In a Python, pure Python environment, you wouldn't need that. Nowadays, maybe you don't even need that anymore in Colab. So basically, we have to import this library, which for string matching metrics, it should be relatively speedy. While this imports, we can just leave this running here. We can go back to find our next steps. So we can go back to what we were given. So here it says we also have to import Sacré Bleu. So Sacré Bleu is a version of Bleu. So basically now we have this imported. You can see the green check mark here. It's successfully done. So we copy this in as well. We run the cell, which is very quick. And here, this is always how we can import, add new code cells. Here it gives us a hypothesis and a reference, but of course we have our own hypothesis and a reference. So what we will do is we can actually just copy all of this, and we don't really need this. The thing is we have our own hypothesis and reference sentence. So either we can adapt this or we can say, hey, I have my sentences. Please adapt the script for me because we would have to change this here. So we could do that. We go back and we copy human reference translation and we paste that in here where it says references. You have to make sure to paste it within these apostrophes because this is pure text now, natural language text, which always needs to be in strings. Then we can also copy, if my screen allows me, the machine translation output. And this will be our hypothesis. We copy that within here. So now we have our hypothesis and our reference. We don't need the comma because we only have one sentence. And let's see if this would already run. Voila. So this worked. So we can see that we have a Bleu score of 26.08. So this is our final Bleu score. And it gives us some more information. So maybe we can go back and ask the system the LLM to interpret the score. So what else did we get in information? A few things to keep in mind. Here it also gave an optional way of running it, which we can skip because it worked already. A few things to keep in mind. Sacré Bleu is a standard library for this. It handles tokenization consistently. Scores range from 0 to 100. So 0 is the lowest, 100 is the best. Real machine translation systems typically score between 20 and 40, depending on the language parent domain. So this is not even a very high range, and we got a score of 26, so maybe that is not too bad. Okay, we can see, let's just copy our score and see what information we get. But also maybe we can copy that these were actually the sentences that we used. I used the following sentences. We copy them in, and I got the score. Can you interpret this? So it breaks it down for us. Bleu 26, the overall Bleu score might seem low, but it's purely because of the wording difference. So automobile versus gasoline station. So this is purposefully done here. We have the hypothesis, they drove the automobile to the gas station, whereas the reference is they drove the car to the gas station. So they drove the is the same in both, but then here we have automobile, here we have car. To the is the same for both, and then one is gasoline station and the other one is gas station. So that's the difference here. It also gives us more detail about the n-gram precisions. So we have a higher overlap on 1 grams and then lower as we keep going. So on the 2-gram overlap, 3-gram overlap, 4-gram overlap. So you can have a closer look at what this specifically means or how to interpret it. We can now compare it in comparison, calculate the TER score. So it already tells us different scores here refers to different scores as well. Semantic metrics like BERT score and COMATE. So we'll also come back to BERT. Let's have a look at TER. I want to compare this to TER. Can you provide the code to calculate a TER score for this example? Let's see what we get here. So TER, then it already describes as well, stands for translation edit rate. Once again, we needed the Sacré Bleu library, which we already have imported, and it gives us a script for this, so we can just copy that. We add it here. Maybe also for clarity, we can add a text and say, here we calculate bleu. We can add a text here and say, calculated TER to have a little order. So once again, here we have our hypothesis and reference sentence, and we calculate the TER score, and now we get a TER score of 25. So let's see what this tells us. So here already it gives us some information. So TER measures the minimum number of edits, such as insertions, deletions, substitutions, shifts, needed to turn the hypothesis into the reference. So what we start with the hypothesis, what we need to do to the hypothesis to get the reference. And then it divides that by the reference length. So the lower the score, the better. So in bleu, you have the range from 0 to 100, the higher the better. Here, it's the other way around. So the closer to 0, the better, because the fewer changes you have to conduct. Well, it estimates that we get around 44. We don't, so let's see. I get this result. It should interpret it automatically. Let's see. So yeah, the estimation was wrong. It was not 44, it was 25. And it says why it is. It's because of these substitutions that we looked at before. And it gives you some more information about it. And then it also says, interestingly, both landed around the same number here. Only 2 of the tokens are mismatched. So you can ask for more information and ask for these scores to be interpreted more, or to compare it more, or to describe more about the metrics themselves. Basically, the idea is here for these 2 string matching metrics that it really just compares word for word how similar the sentences are. But we know, naturally, that these sentences are pretty similar because automobile and car refer to the same object, and the same counts for gasoline station and gas station. So technically, these sentences should be ranked as quite similar in quality. So let's have a look at BERT score, which is a different type of metric. We'll add this here as well to have a little order. So now we're not looking at a string matching metric, but an embedding-based metric, and you can read much more information about that as well. Let's see what we're being told here. So we'd now like to calculate BERT score for this example. Please provide me a script. So embedding-based metrics, well, let's pretend we don't know. Okay, it doesn't tell us anything. We could ask for an example. Let's see if it describes. Okay, so It already describes it a little bit here as well. BERT score uses contextual embeddings based on Google's BERT or RoBERTa to compare tokens semantically rather than by exact match. So synonyms like automobile and car or gasoline station and gas station will score much closer to each other. So if you would want to know more information about this, um, you could look up more information about it or ask your system, your model more about it. But basically what it means is that before the word embeddings, we weren't looking at word embeddings, at contextual word embeddings, just pure words, the similarity between the surface level of the words. And now in contextual word embeddings, it understands that these words actually have similar meaning. So yes, this score should be much higher. So we can copy this all in one. Usually it's a good habit to have this separated. So we copy this and pip install BERT score. And this might take a little longer than BLEU because yeah, it's a more complicated computation that is required. Okay, that went really fast as well. Nice. So we can add a new code cell and we'll copy the rest of this. So then we can delete this and we'll just run the cell. So once again, we have to import something from the library. Then we define our hypothesis, we define a reference. And the thing with the BERT score also is that it would provide us three scores. So we will get a score for precision, for recall, and a combined F1 score. And as you see, this loads a little longer. So maybe in the meantime, we can go back and have a little look what this means. So it gives us a score for precision, how much of the hypothesis is semantically covered by the reference. Then it gives us a score for recall, how much of the reference is semantically covered by the hypothesis. And it gives an F1 score, which is the harmonic mean of the two. So this is the main score to report. So this is what we will be looking at. Here the prediction is that we'll get a relatively high score, F1 score. So let's see what we actually got. It provides a lot of information, but all we need is this information at the bottom. So we can see we get a precision score of 0.9785, the same for recall and therefore also the same for F1. So maybe actually, yes, we copied this. Can you interpret these results? Copy them in, and let's see what we get. Great results. All right, why precision recall? Why they're all the same. All three are identical because both sentences have the same length. Both the hypothesis sentence and the reference sentence. Usually sentences have different lengths. And then it also goes to explain BERT score computes pairwise cosine similarities between all token embeddings in both directions. And since the lengths are equal, the sentences are almost mirrors of each other. So the scores are perfectly balanced. And then it describes, okay, what does this score actually mean for us? The score is very high, so close to 1. So here we have scores between 0 and 1. So the higher, the better again. And it goes to describing a bit of, yes, what this means. So you can read more about this. It gives you a comparison here as well of what it means. And here, once again, we see, yes, the BLEU score is harsh because it penalizes synonyms. It doesn't realize that it refers to the same object. This is moderate. And then this one is much more accurate. So we see that a metric that is based on contextual word embeddings performs much better here for this task and also for many other tasks when evaluating quality. You could also now ask to calculate this all at once to provide a cleaner format. This is also not a very clean way of writing it technically because we always refer to the same hypothesis and the same reference. You could define these sentences once at the top and then import everything also at the top and then go down and just calculate the individual scores Now we just copied the hypothesis and reference sentence every single time because we just copied the output. But we started from scratch. We didn't know what the scores did or how we could use them, how we could apply it, how we could interpret it, how we can compare them. And now, just by having a quick back and forth with my chosen model, we could do all of this. We could run it. We didn't run into any errors. And if we did, we could ask the system, help, what happened here? Please fix this for me. So this was a very smooth process, and we have successfully computed scores and interpreted them. So good luck with the rest of the exercises as well.